Hello, this is Professor Urban, and today we're going to learn about ellipsometry measurements on indium tin oxide, transparent conductive oxide, and the idea is to get more out of the measurement, get a better solution out of the measurement. So let's jump right in. In order to organize this talk and video clip, I have made a set of notes which are concurrent with the actual presentation itself. So I will not show these until the very end, and I'll show each page for a brief moment in case anybody wants to refresh their memory or review it later. So we start. The numerical ellipsometry, this idea of using numerical methods to improve the amount of accuracy and information that can be obtained from a set of measurements, which sadly is left out in some other techniques for making that conversion from measurement to solution. And the co-author on this is Professor Barton and at FIU. And I will have to remove my face because it's in the way. So this talk focuses on the measuring, modeling, and solving. And we're going to talk about how that can make an improvement. And it turned out to be multi-layer. A brief refreshment on ellipsometry, the idea being light is brought in to be incident upon a reflecting surface, whereupon it does reflect, and it's polarized in such a way, plane polarized, and in such a way that the perpendicular polarization, that is perpendicular to this plane of incidence defined by the incident and reflected rays, and the magnitude of the parallel component are equal. And upon reflection, and there's a certain incidence angle, you can vary that in the instrument. You can also vary the wavelength of the light. This is done at one wavelength. What happens is that when the perpendicular component reflects, it undergoes a change in magnitude and phase. The same is also true for the parallel component. In general, the change in magnitude and phase are different, and so we end up with the exiting wave or the reflected wave with them out of phase. So we no longer have a plane polarized wave, we have an elliptically polarized wave. And if we examine that, and that ellipticity contains useful information about the surface that's doing the reflecting. So if we take a closer look at this, this represents the reflected wave, and we can see here, in the way, that if we look straight on the z-axis hitting you in the eye, you would see that the ratio of magnitudes between the two reflections can be represented with the term psi. And at the same time, the difference in the phase can be represented as a term delta. So one measurement at one wavelength provides two real numbers, psi and delta. That's good. This is a graph of a measured value of psi for a wavelength range from 200 out to 1700, and at three different angles of incidence set for the instrument. Blue is 55, green is 65, red is 75. And you can see that the value of psi is ranging from 0 to 90. Makes sense if you think about the prior figure. And that it's different for the different angles of incidence, and we hope to take advantage of that in doing a solution. And it's quite a interesting looking wiggling curve. We can, each dot represents a measurement. This is the same basically axes, a horizontal axis for wavelength of the light, and the vertical axis is the angle delta, and delta is the phase shift. So that phase shift can go, if it was psi is bounded from 0 to 90, delta can go whatever it needs to go. And so as you can see in the green curve, that when it hits a certain angle, it has to be, you take off 2 pi and start over. So these big jumps in the green curve are not actual measurements differences, but they're jumping to a different angle because of the nature of the function. So they're not very smooth, and matching that up to a mathematical model that includes the Maxwell equation, you know, that's the crux of it, right? That's the hard thing. Getting the measurement isn't easy, but matching these measurements up to the Maxwell equations so that you get a consistent value. What we're looking here is for the optical properties n and k, or alternatively permittivity. If you have one, you have the other. So what are the equations in the mathematical model between the light incident and reflected and the materials involved in the reflecting surface? This is a schematic in the upper left here of the reflecting surface. It shows surrounding medium as an index of N0, which is air or vacuum. It's going to be 1. And the substrate, in our case, is going to be silicon, so we know that. It's well tabulated and well understood. What's not known is the thickness of the reflecting layer, D, nor the index of refraction, which is in general a complex number. So we have here 3 real number unknowns that we need to extract in this process. So just take a glance at see the nature of these equations. They're shown here is the Snell law, which tells you something about the incidence angle and the refraction angle. I'm not going to say detail about this. These are the Fresnel equations, which give you a value of the reflection coefficient at a particular interface. So at this interface here, and the parallel component reflects one way and the perpendicular reflects another way. S for senkrecht is the perpendicular, and P parallel. And you can see the values of the unknowns showing up as we go along. N1 is appearing in all these things. And then if you want to take reflection off of a film, you have to consider an infinite series of reflections, add them together using an infinite series expansion. I will not go over that here. Well, I could. And we end up with a more complicated equation, which involves these other equations for single interface reflections. And we end up with what really quite a complicated equation. Fair enough. And it's something that we can't easily solve front to back. In other words, writing an equation D equals some function of sine delta, that's not doable for this. It's doable for a soap bubble, as demonstrated by Azam years ago. And that's it. And we have to solve this at every single wavelength that we have chosen. And here is an example of an attempt to do that and to match the Maxwell equations to the measurements. And what we've got here is a model of the reflecting surface. In order to cast the Maxwell equations, we need to have a model of the reflecting surface to start with in this case, and in any case. So we have to fit the equations and a model to the measurements. So the model that eventually got settled on for this particular solution was a silicon substrate here at the bottom, air up above, not indicated in the figure. This is not a layer, but it's a way of incorporating some optical properties into the modeling program, the Willem program. And then the 2 layers that make up the reflecting film. One layer, the second one, is a graded film, meaning that the value of the index is varying little by little as we go up through it. And with a thickness of 358 and change nanometers. And then on the surface, not surprisingly, it has some roughness, and they have modeled the roughness here as being 53 nanometers, and I believe 50-50 air and materials. So this compensates for the fact that the surface might be rough. I don't think an attempt has been made to look at that with atomic force microscope to see if you actually can get that roughness measurement off the surface, but nevertheless, it's the model that was used. And if you look down below for the 3 different angles of incidence, you can see a remarkably good outcome, which is that the green dotted lines, which are the 3 experimental data sets, are matched quite nicely by the 3 red lines, which are the model fits. So using this model and the Maxwell equations, you end up saying, wow, this funny looking measurement curves, I'm got it, I'm close. This must be it. And it's close. But if we actually subtract the measured from the computed, we find out it isn't very close. I mean, here and there it's pretty close. This is 0, and you can see that it's close to 0, but the measurement accuracy of psi of the instrument is in the fraction, it's in a few hundredths of a degree in that order. And we are way, way beyond that. I mean, we're 10 degrees off here at certain wavelengths, and we're way, way out of the accuracy that's in the data. So this is not a good fit. And it's a fit, not a solution. It's done by Levenberg-Marquardt damped least squares, if you must know. So we can see right away from our own result that it is not taking the full use of the instrument accuracy. Here it is again showing delta for completeness. Psi and delta are measured simultaneously, as you saw a moment ago. And it's amazing that it does a pretty good match to these rather odd looking curves. And over here it's a little harder to see, but they're missing by a lot. And it's the same model, same process, and you can see that we're missing the measured and computed difference is way over the 100th of a degree or so, a few 500ths of a degree that we have for accuracy in the delta out of the instrument. So, I mean, look at this. It's 90 degrees, 60 degrees. It's a bad fit, but it's the best that could be done. So our goal here is to find a better way to make use of the data, and the reason that this fitting is such a problem is that we're looking for a minimum in an error surface. And I'm going to use this as an example of what that would look like in a real life situation, not of finding a math problem, but of what could be an error surface. Fair enough. And so my little way of showing that is to say, let's say that we're going to start here. We're looking into the great unknown. We're starting at a certain point, and we're going to try to find the bottom of the Grand Canyon by starting at a certain point, and all we have is a flashlight, which lets us see a little bit around where we are. It's the slope of the land where we are, and an altimeter to know if we're going down. And that's what the solution process looks like in least squares. And it works great depending on the circumstances, and it's totally legit good way. But looking for the bottom, is it here, is it there? As an aside, I must tell you, I took this picture myself. I had just been climbing up out of the canyon. It was a beautiful December day. We'll be groping about with that flashlight and the altimeter, and here's part of the reason. When you're doing this technique, there's no defined start points. You have to figure out your start points by trying different things. There's no topo map. It doesn't tell you what routes you should be trying to follow. There's no positive confirmation you've got to the bottom. I mean, this looks like it might be the bottom, right? Because everywhere around you is up, so maybe that's the bottom. Maybe there's a bottom. These are called local minima, and we're looking for the global minimum. So, and on top of that, it's a fit. So you're trying to fit all of the measured data points at the same time with all the computed data points in a least square sense. It works, but it doesn't work well for certain problems, and this is one of them, I believe. So to continue the analogy, we'd like to add a few things to our bag of tricks here. We would like to have a topo map that shows you the lay of the land that you're going to be exploring with your looking for the solution, not a fit. There are trails on the topo map. You can be on this trail. I don't think it's good to be off the trail. There are starting points, and when you're there, you know you're there. There's a solution. So we want to do the same thing for ellipsometry. In this case, we will produce that figure in a different way for the ellipsometry problem, and we'll do it by plotting on the vertical axis K and on the horizontal axis N, optical properties of a material, and the thickness is varying along the curve. And basically what we're saying here is that at any given measurement, and here are the measurements, at this particular measurement, for measurement number 1, this point here is equally valid a solution as any of the points along this line. And along that line we have varying, you can see K and N are varying, but D is varying in the Z direction that's poking you in the eye. So every point along there fits with great accuracy the Maxwell equations. Now if we go to a separate measurement here, measurement number 2, we're going to find that it traces out a different curve through the NK plane, and according to the fact that it's being done at a different angle of incidence, and so on, for 3 different angles of incidence, or they could be 3 different thicknesses. You have to do different things, and you'll see that, wow, they do intersect somewhere, and where they intersect has to be the solution. You might end up with 4 different thicknesses here, but you've got the same N and K, and it confirms that the material isn't changing with thickness, for example. It's part of what's required for this to work. This was on chromium on silicon data. And we see a nice sharp vertex. Ta-da! We're looking for a mathematical solution now, not for a fit. And it's done at a wavelength, not at a set of wavelengths. So let's turn to the ITO. In the case of the ITO, I had 3 wavelengths to work with, 55, 65, 75, and plotted the solution curves and immediately disappointed. The curves are so close together. Finding their intersection is, well, computers can find intersections of things. And if we can expand it out and take a closer look at where they are crossing, indeed, you could find that, but you can see that it's not crossing in a crisp way. Why not? Well, it could be the measurements. I doubt it. They're quite accurate. It's probably the model. So we're going to miss a little bit on that. Meaning the model is, we're assuming a single layer model with no interfaces to get these curves. Much too detailed for us to go into now. But assuming that, we see not a sharp vertex. So how are we going to know how to sharpen the vertex? Let's give that a go. That vertex is livable, but if you take a closer look at it, it has its shortcomings right there. Now this is a close-up view of that near vertex, and it's a little triangular region, and the 3 different colors correspond to the 3 different measurements at different angles of incidence. And rather than a single line, you'll see 9 lines. You can't really see them individually. Well, there's the central line, which conforms to the measurement, and then there are plus and minus values for psi and for delta. That so you have plus psi, plus delta errors so that you can see what the reported by the manufacturer experimental error gives us as a range of values of the solution curve. And you can see the three ranges, broaden it out into what we call these solution curves. So that's useful and interesting. And then if you look here, this intersection is the far left and this is the far right of the three intersections of two curves, and they're not lining up very well. And you can see that the error here, we'll call this as the model inaccuracy. If the model were perfect and the film were made perfectly that way, they would cross, but they don't. So the film must be something a little different. Fair enough. So you can see they're not horrible. I mean, the delta in the K is, this length of red line means delta K is about 0.005, so we're getting that nailed down pretty well. And delta N is also 0.005 in that direction, so it's less accurate in N and more accurate in K. Well, I want to go better than that if I can. But nevertheless, I will go ahead and apply this, and picking one particular wavelength, 730 nanometers, gave us a thickness of 401.5 nanometers as being the kind of the average thickness of where those three intersections take place. And you can, this is a detail, but this is how you interpolate any given solution curve to find out what its N and K would be. So now we're going to take this number, go back, interpolate on all the different solution curves at each measured wavelength, and get a value of N and K for each of them. I hope that's reasonably clear, but when we're finished, we'll end up with a red, blue, and a green curve for the three different angles of incidence. They don't exactly agree, but they're pretty close. Good. This is a little area where measurements weren't made, and we'll talk about these across wavelength here momentarily. So in this region here, from about 950 out in wavelength, you'll see something interesting if you take a look, first of all, at the curve for K. Let me see if I can fit in there. No. So you can see that the value of K, this line is K is 0, so over here it's transparent, but over here it's not, it's absorbing. And these numbers of K, 0.51, 1.52, are characteristic of a metal. So it has a metallic behavior optically for that range of wavelengths. And you'll notice also that the value of N is dropped below 1, and that is also characteristic of various metals. So it looks kind of like a metal. It's opaque, increasingly opaque in that range of wavelengths. In this range of wavelengths, it's transparent. The value of pretty close to it, and the value of K is near 0, just like window glass. And the value of N is descending from around 2 to around 1 1/4. That's also like of a transparent material like window glass. And interestingly enough, there's a little region in between them, a transition region, where there's actually good condition. We'll see that momentarily, and we can get more data, more information out of this than we can in these other two regions. So the answers in there are a little crisper. And then if we go to the short wavelengths, you can see the solutions don't look very good, and it's easy to see why. If you go ahead and look at the intersections, we find out we probably need to model it with 3 layers in that wavelength range, and we just don't have sufficient number of measurements to get good solutions there, so they're not going to help us. And they look a little bit like it might the numbers that you might get out of a semiconductor. Okay. And we try, and now eventually get an answer. And here is the answer that we get. This is now not using the earlier method. The earlier method being Levenberg-Marquardt, variably damped least squares, fitting. This is using the NK plane, and looking for intersections and a mathematical solution. And it's more accurate. Here's our, the proof is in the pudding, so to speak. Here, you'll see it in the next slide. But here are the 3 angles of incidence and the 3 sets of measurements, and you see right here on this curve the measured and the computed, and you just can't see any difference between them. And for interest's sake, I divided this wavelength range up into the longer, where you see the more metallic. We understand now that's going to be more metallic. Across the middle section, we're going to recognize that as being transparent, and this is typical of transparent media. And something different at the shorter wavelengths that we don't have a good handle on because we don't have enough measurements in that wavelength range. Let's now subtract the two, and let's look first of all at the same thing for delta. And for comparison, this was the subtraction. I didn't look at that long enough, did I? You just can't see the difference between the measured and the calculated, done in the NK plane. Okay, let's go back and refresh our memory. How did things look for the least squares Leavenworth-Marquardt method fitting? And the answer was not so good. The differences between measured and calculated were huge, way more than the measurement accuracy of the instrument itself. And we end up with a mean square error of all these data points of 34. Comparing that to the solution using the NK techniques, which I've been describing, we have a vanishing mean square error. It's not 0, but it's very, very small. And you can see on the graph here, same vertical axis as before. Let's refresh our memory. So we're going -10 to 15. And here we're going -10 to 15, same vertical axes. They're apples to apples. And you can see that if I subtract the measured and the computed, we get almost nothing. So we've really used the data well to get that kind of a fit. And this is the fit that we get from that data that I showed you a moment ago, listing n and k as a function of wave number. So this is not anything peculiar to look at. Let's take a look at delta, same thing. I won't belabor it. The differences are huge when you're using the least squares approach to solving this problem. Fitting. If we use the NK method and look for intersections in the NK plane, we find again a vanishing mean square error. Not really, but very, very small. And if you make a graph on the same axes, you can barely see the difference between the measured and the computed. So clearly it's superior. And a very interesting thing happens in that transition region. In the, you might remember from before that the 3 solution curves were quite nearly parallel, and it was hard to get a real crisp intersect. But it turns out that in the region of 900 to 990 to 1,000 nanometers or so, that one of the solution curves flies in from the left and the others from the right, and at big angles, and we have a chance now of a much more accurate investigation of the area where they intersect. Good. The condition, mathematical condition, is good. What are we going to do with that? Well, we've got 6 unknowns. If we add another layer, we add 3 more real number unknowns, which would be another thickness and n and k for another layer. So we'd have 2 layers, 3 unknown numbers for each, and we're making 3 measurements with 3 pairs, psi and delta. So it should mathematically, we should be able to do that. Let's see what happens if we do that. Well, before that, I also want to look at in the DND plane. I don't usually do this in the ND plane, but just to see if, is this realistic? Are they coming to the same thickness when they do that sharp intersection? And the answer is yeah, they are. So we've got something that we can work with here. A real live intersection with good mathematical condition. And P.S. by the way, we only have to solve for these thicknesses at one wavelength. They're going to be the same at all the wavelengths. So we could take this information and apply it to the other wavelengths, and very handy thing. So if we now model the film as 2 layers rather than 1, and then find a lower layer that has a value of 99.2. Remember, the overall was 401.5. Now we have 99.2 nanometers attributed to a second layer. Now I'll refresh your memory that the first model was a graded layer model for the least squares, and that meant that the value of n and k varied as a function of thickness. And so it shouldn't shock us that we find another way of modeling it, and this time rather than with a multiple number of layers, but 2 only, and that's all we can solve mathematically for this. But 2, and one of them we get 99.2, and the rest makes up to the 401 roughly. So, and we get a value of n, and that's only at 990. We can't get these other values easily for the other wavelengths. I'm sorry, I've been working in the IR lately. But you can see a really great intersection here. It really brings it down to a vertex. So we don't have the triangle anymore. We have, practically speaking, a solution, a mathematical solution for the 6 numbers. And here we go, zoom in and take a closer look at the solution tubes and where they intersect there. I picked 1,000 nanometers just to show another nearby wave number, and you can see them coming through at respectable angles. That means good condition in the solution, and you just can't make it any better than this. You could, but only if you could make these solution tubes narrower, which means more accuracy out of the instrument. But these are really, this is the instrument, the model error is really quite small, 0.002 roughly in the K direction, and in the N direction, if we look at the, I don't know where to actually measure it from, but you can see that the axis is quite small. So we're down into the hundredths, numbers of hundredths in N and K for that solution. That's a triumph. So we can't really improve on this with this data set, because you can see the solution tubes. We've used up all our accuracy, and we've used everything we've got at that particular wavelength. So our conclusions are as follows: that this had a transparent region, its absorption of metal-like. Once we reached 500, we found that the NK plane method can work with ITO and 3 angles at that thickness. Now, if it's very thin, we've found that that may not work, but it does work here. It would be better if we had films of varying thicknesses. We'd have more information. Good. Higher order features were just not accessible, and it shows that we have at least with 2 or 3 layers of ITO. And that's it. So I will now go back to the outline, and we'll just review it via the outline. So what did we do here? We are talking about ITO and an advanced way of making measurements on ITO involving intersections of solution curves in the NK plane, a numerical method of its own. And we do end up comparing it to the Lemberg-Marquardt standard method, which is a perfectly wonderful method, but it doesn't do the job for us here and doesn't get the measured and the calculated numbers to agree very well. So just to review what the slides covered one by one, and leave it up there long enough for you to write things down. We started off talking about the reflection geometry and ellipsometry in slides 2 and 4. I guess that should be 3. And then we had measurements of delta and psi, and looked at their squirrely look, and then we looked at fitting and using a graded layer and a roughness overlayer, and we ended up with a mean square error that was big. And the matching measurements to the model in the least square sense, we don't want to do that. We want to go to more accurate, and I use the Grand Canyon as an example of what you're fighting with least squares. Multiple solutions with, that is, local minima, and not knowing where to start the process. It can get lost and diverge. We didn't even talk about that. So the NK plane is a way of tackling this, of plotting a given solution for a single film is going to be NKD, 3 unknowns. We went through the math for that. And if you have 2 measurements and 3 unknowns, then you can't uniquely get a solution, but you can get sets of 3 numbers that match the math. That's what we did. We did it for 3 different angles of incidence and found out that they intersected. And if we considered the error, we ended up with solution tubes. And we could figure out, okay, the overall accuracy and the instrumental accuracy, and look at the intersecting region. Doing that for ITO, we find that there were regions, there was a wavelength in which it was metal-like, transparent, and transparent here, and so on. And that by comparing the psi measured and calculated with the 2 techniques, one Levenberg-Marquardt, one of them the NK, we find out that you're using the data with the NK approach. And we examined that by looking at the difference. Oh, I went too fast. Maybe you want to have that there for a moment. If so. And then looked at the solution curves for various and sundry wavelengths and made a set of conclusions. So on that, I will flip to myself and tell you I hope you learned a lot and that it was fun to do this, and to show you that I have on one of my favorite ties, which I like to wear at conferences where there are people from all over the world, to let them know that I know about the United States, but what about Brazil? What about other countries that are important? I hope you learned, and if you did, I salute you.